Anyway, this is Sanjeev Reddy, and I did my MTech from IIT Delhi, in fact. So from that, so I've been in this field, teaching field, for past about 7 years. And before that, I worked as a scientist in BARC. Now I'm working as a research engineer in one of the corporate companies. I have some papers as well, IEEE and IEEE papers, right? So anyway, so I'll be teaching you electrical machines. So the content of the electrical machines here, the syllabus. First we'll see the syllabus, what it has. Then we'll go in detail about the subject, electrical machines. So in this, I'll be discussing with DC machines and the second one I'll be discussing with synchronous machines, and third one I'll be discussing here about transformers, fourth one induction motor. So in this DC machines here now, of course 1, 2 and 4 are rotating machines. You can see all these kind of thus 1 and 2 and 4 are called as rotating machines, and the transformer, which is a kind of static piece which is stationary, which won't rotate here now. And then if you look at the AC and DC machines, the first one is a kind of DC. This is DC. And the remaining 2, 3, 4 works on kind of AC. And again, when I say AC here now, among AC, we'll be having a single phase as well as a kind of 3 phase here now. So if you consider here now, the single phase or kind of 3 phase, we'll be discussing the synchronous machines. Most of the things, synchronous machines are kind of 3 phase. Of course, the single phase also will be discussing under the fifth one, which is called as a fractional HP motors. Fractional HP motors are kind of a single phase motors. We can call half HP motors are having a low wattage. In this case, most of the things are of single phase, maybe single phase induction motor, single phase synchronous motor, all those things we'll be discussing here. That mostly comes under the single phase. And the transformer, for your syllabus, you have single phase mostly. 90% of the syllabus is confined to single phase, and 3 phase is very limited. Anyway, we'll be discussing that as well there. An induction motor. An induction motor is a kind of, again, 3 phase. We can discuss that as well there. And fractional HP motor, under fractional HP, again, single phase induction motor we can discuss here now. So this is what you have in the syllabus. And the percentage of marks for the gate. See, you always get one question in the DC machine. Maybe it can be 2 marks or 1 mark. Mostly it is 2 marks question, which is a problem. Or 2 plus 1, 3 marks you can get. And most of the questions are again from synchronous machines and the transformer, because we can't guess the questions from the synchronous machines, transformers, induction motors. So it can change. Sometimes it can be 2 marks, sometimes 4 or 5 marks. It will be changing, but I can guarantee that a DC machines always get a minimum or 1 question definitely will get in the DC machine here now. And for about the syllabus, content of the syllabus, when the DC machines is done, your 60% of the syllabus is almost done, or maybe 50 to 60 I can say. 50% of the syllabus is over if the DC machines is kind of done, and the remaining 2, 3, 4, 5, the syllabus is very less or limited, I can say, compared to the DC machines here now. Anyway, we'll discuss one by one, and if you have any doubt, you can ask me, not even a simple thing also. When it's a simple thing here now, even you can ask me something like 2 plus 3, which is equal to 5. You can ask me how it is also. Such a simple thing you can ask me. I can even explain better how the 5 comes here now. But anyway, we'll go in detail here now with the subject. And DC machine. When I say DC machine here now, all my synchronous machines, even in synchronous machines also, it consisting of generator and the motor, synchronous generator, synchronous motor. Here also here, I'll be having a kind of DC generator, and I'll be discussing your DC motor as well there. And among the DC generator, if you discuss the DC generator here now, so the DC generator principle. Before going to the principle here now, maybe the simple construction. What does a generator do? Any generator will do, it try to convert your mechanical energy to the electrical energy in fact. So if you take a kind of any machine, let it be when you try to kind of give the mechanical input to that machine, and then you'll be getting electrical output here now. So look at here the construction, two parts are mainly here. I'll be having a poles, of course the magnetic poles. The second one is kind of conductors. Poles are magnetic poles, second one is a conductor. If these two are existing, then your voltage can be induced. So meaning here now, if I take before going to the exact construction of the machine, for example, if I take a kind of normal magnet, when I say poles here now, the poles, magnetic poles will come from a magnetic bar, so which consisting of two poles which are north and south here now. And if you take a kind of conductor, maybe a conductor can be a wire, normal wire. If you take a normal wire, the normal wire you can wound it as a kind of inductor or whatever it may be, like a coil. I'm just making this a kind of coil or a kind of simple conductor and something like this. And to this, if I connect a kind of any galvanometer to this one, galvanometer is the one which senses the kind of current which is flowing in the conductor if it is kind of closed there. I just connected a galvanometer here now. So what it happens here now, if you just try to move this conductor to and fro, then the galvanometer starts, the pointer of the galvanometer starts kind of moving left or either left or right side, which means that there is a kind of current which is flowing in the conductor, which means there is some voltage which is induced in the conductor there. So that's what I'm trying to say. There is a magnet and a conductor. So whenever there is change in a conductor position, then the change in flux will be there. I'm using a word flux. Flux in the sense magnetic flux here now. So magnetic flux in the sense, you can see the north and south pole here now. So it has magnetic flux lines there. Look at here now, the magnetic flux line, something like this, north to south, and inside south to north, and here also here now, and something like this here now. So these are the kind of magnetic flux lines. So now what happens is when the conductor comes and cut this conductor, I'm using another technical word which is called as a cut. So when this coil comes and cut this conductor, for example, if this conductor is kind of coming over here now, for example at this position, and it cut only one magnetic flux, blue line. And when the same conductor kind of moving towards here now, it can cut 2-3 flux lines there. So change in flux is occurring here now. So as the position changes, as the conductor moves towards the magnetic field, as the conductor move away from the magnetic field, so there is a change in flux lines occurs in the conductor, then the EMF is induced. It's all about a kind of principle of generator, or we call it it is called as a kind of Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction, what it says in simple, I can say the EMF induced in any conductor is directly proportional to minus d phi by dt, or I can write E equal to, which is equal to minus n d phi by dt. So this is your kind of EMF equation, I can say, or the Faraday's laws of. So Faraday's laws of electromagnetic induction here now, the EMF induced in the conductor, which is E, is given by E equal to minus n d phi by dt. So, and this is whatever I explained is a conductor, a pole here now. Two poles, it can be, number of poles can be increased also here now. The meaning of minus sign here now, E equal to minus n d phi by dt, when the conductor is kind of moving towards a magnet, towards a south pole. What happens is, as I mentioned, the change in flux occurs, the flux lines cut by this conductor are changing. Then EMF is induced. When the EMF is induced, the current is flowing in the conductor. When the current is flowing in the conductor, the current carrying conductor will produce a magnetic flux, meaning coil also will act as a magnet. The magnets are formed such a way that your polarity will be something like this here now. Look at the polarity. When you're trying to move towards the right to left, south pole is formed, north pole is formed here now. So there is a repulsion. So whatever the action that you are trying to do is trying to oppose here now. So because of that opposition, we are making is minus sign here now. Again, similarly, yes, when you are trying to move back from my left to right, then the polarities are formed here now such a way that yes, here is a south pole. When you try to move away from this one, and if you already kind of south pole here now, you already have a repulsion. Again, if a south pole is formed, again you are giving a extra force you are giving here now. So again here also opposition, so that the polarity formed here is a kind of north and south here now. So again north and south are formed, so that you are trying to go away from the magnet, but this magnet is trying to pull you inside. So ultimately what I am trying to say, whatever the action that you do, the opposition action will come from the kind of magnet. Opposition action will be coming from, because of that minus sign will be there. Even that also was in, if you try to walk on a floor, you get the equal and opposite opposition. Otherwise you can't walk. If the road is slippery, you can't walk. So that's because of opposition. So when you have an opposition, then only the work is said to be done. So that Lenge's law, which is a minus sign, as I mentioned here now, we call as a Lenge's law. So it is, the minus sign represents a kind of Lenge's law. So this is a basic experiment that I have done before moving on to the construction of a generator. So what I explained, a magnetic pole I have taken, a conductor I have taken, the conductor I have moved towards the conductor to and fro like this, left and right, then the EMF is induced. You can ask me a question, why only magnet is moved? Why can't you move, why a conductor is moved? Why can't you move a magnet? Yes boss, you can do that. So you can just keep your conductor stationary like this. So just you can do this one. I have my conductor which is placed here now, and a galvanometer is connected here now. This is stationary. And now I have now the magnet, north and south. So what happens? You start moving this magnet here now. If you move this magnet here now, the number of flux lines will cut by, because the distance between a magnet and a conductor is changing. So the flux lines are getting changing. So then the change in flux occurs, EMF induces. And next position also you can have the change in flux to and fro. This is stationary and this is moving. So the EMF is induced in the both ways. Yes, you can do both the ways also. Conductor is moving, magnet is moving, both the EMFs can be kind of induced here now. But we have some different names here. The way the EMF is induced. For example, if the conductor is stationary and the magnet is kind of moving here, the static EMF we call it. This one is a static EMF. And if the conductor is moving and the magnet is stationary, we call it a dynamic EMF. Two terms. Dynamically induced EMF if conductor is moving. Otherwise it's static EMF, statically, which is stationary, which is a kind of transformer EMF. We call static EMF. Otherwise static EMF. Static EMF can also be called as a transformer EMF. Transformer EMF.